Okay, hello everyone. Welcome to the LTI Colloquium. Today I'm very happy to introduce our guest speaker, who is Jacob Andreas. Jacob Andreas is the X-Consortium Assistant Professor at MIT, and his research aims to build intelligent systems that can communicate effectively using language and learn from human guidance. And Jacob earned his PhD from UC Berkeley, his MPhil from Cambridge, where he studied as a Churchill Scholar, and his BS from Columbia. As a researcher at Microsoft Semantic Machines, he founded the language generation team and helped develop core pieces of technology that power conversational interaction in Microsoft Outlook. And he has been the recipient of a Sony Faculty Innovation Award, Colloquium, for teaching at MIT.
I've never heard it spoken out loud, so I have no idea how it's pronounced.
And paper awards at NACL and ICML. And I tried to add a personal anecdote, which is one of the first papers I know from Jacob is on globally normalized models, which Jacob probably hasn't thought about for several years now, but I've been following his research from early in his PhD career, so very nice work, and I'm looking forward to hearing the newest of it. So.
Cool. Yeah, thank you very much for the introduction. Hi, everyone. So what I wanted to talk about today was really using language as a tool. And as a tool not just for training models in natural language processing, but a tool for training machine learning models really kind of across application areas. And I'll say at the beginning, I guess this is like quite a long slot, so please ask lots and lots of questions during the talk and interrupt me whenever. Cool. And where I want to start with this sort of big question of using language to train other kinds of machine learning models is with the very big question of how people learn. One of the sort of distinguishing features of human cognition, right, is the ease with which we acquire new concepts and skills. And we do this in a number of different ways, right? When we're lying in the crib, before we even really have the ability to manipulate the world at all, we learn just to like compress what we've seen and to predict what's going to happen in the future. Once we gain the ability to act, we learn a huge amount from interaction with the world, right? From exploration, from trial and error, and so on and so forth. Once we know a little bit about our social environment, we also learn from explicit labeling and demonstration, from sort of teachers with whom we're sharing attention and sharing focus. And finally, once we have language, we learn a lot from language. And it's the last of these things that I really want to focus on today. The number of things that we learn about the world from language is enormous, right? We learn sort of factual events, we learn dates, we learn important historical events, we learn names of things from things like dictionaries, from things like definitions. We learn procedures like how to cook or how to do, sort of more complicated things like how to program from books that describe these procedures in natural language. We learn even information that extends our knowledge of language itself from knowledge communicated linguistically, like dictionaries and things like that. And probably most of us who are in this room today got here by listening to lectures, by reading books, by talking to colleagues. And so this, seems sort of fundamental. It's, of course, very hard to get to the point where we can do all of these things. We rely on the ability to learn in all of these other ways to bootstrap our understanding of language in the first place. But once we learn language, it's language that really plays an important role in learning these like most complicated skills that we have access to. The ability to learn from language is in some sense one of the like fundamental things that separates us from all of the other learning systems that nature has ever produced. It is also one of the things that separates us from all of the learning systems that people have ever produced, right? All of the other categories that we had on that first slide, sort of learning from observations, we call unsupervised learning. It's a major topic of textbooks and conferences and so on. Learning from exploration is a major topic of research in machine learning. We call it reinforcement learning. Learning from demonstrations, supervised learning, major subject. But not so much this last category. And so what I'm going to be talking about today is really just like a couple of very first baby steps towards making language a first-class tool for training machine learning models in the same way that all of these other things are. Okay, so first off, why has it taken us as long as it has to get to this point, right? Why haven't we filled in this chart already? And I think the sort of fundamental reason, right, unsurprisingly, there's a bunch of other skills that you need in order to get to the point where you can use things, where you can learn things from language. There are two of these that I want to call out in particular. The first of them is the ability to understand language, right? What words mean, how words fit together. Sort of fundamentally, if we're going to use language to understand other things, we first have to understand how to use language itself. And the second of these is representation learning. And specifically the ability to learn multimodal representations of concepts that integrate, for example, linguistic information and visual information and control information, right? If we're going to use language to supervise other kinds of machine learning systems, we need to figure out how language grounds out in all of these other application domains where we want to be able to supervise models. And I'd argue that it's really like just in the last few years that these tools have become, certainly not solved, but mature enough that we can start to think about applying them in other application domains. We now have pretty good off-the-shelf tools for producing structured linguistic representations, right? Representations of syntax, like parse trees, representations of meaning, like logical form, that are going to give us access to the underlying structure of language in a way that we can hook it up to these other tasks. And we certainly now have like pretty good general purpose machine learning tools for constructing shared embedding spaces in which representations of images and representations of policies and representations of strings all kind of live together and talk to each other. And sure enough, as these tools have become mature, we've started to see some initial approaches to natural language supervision, building on both of these things in specific contexts, right? So on the sort of using these structured language understanding tools to help with other tasks, there's been some work that I find really inspirational, actually, from Tom's group here by like Igor Labutov and Bishan Yang on learning, and Shashank Srivastava, I think, on like using semantic parsers to construct logical representations of classifiers that then help you with classification tasks. And then on the other side, on the representation learning side, like really since the earliest days of deep learning models for computer vision, or at least the like current generation of deep learning models for computer vision, the vision people have been using representations of words and representations of sentences learned from big text corpora as auxiliary supervision for models that are just doing image classification. And if you've seen Clip and Dolly are like the biggest and baddest recent versions of these things, but this is an idea that's at least a decade old at this point. And so what we're really going to try to do today is to take this foundation, right, provided by this existing work, provided by these existing tools, and scale it up into something that can in principle solve, the even more complicated problems that we want to be able to solve with the machine learning toolkit across application domains. The first of these things, and we're now into the outline of the talk here, is learning models that don't just make one-off decisions like classifiers do, but that actually interact with the world and sort of reason about future actions. This is something that shows up everywhere, right from dialogue systems to robot control policies. And so we're going to start at by looking at a technique for using language to learn reusable skills for planning and acting in the world. In addition to decision-making, another sort of key core problem, maybe the other key core problem in artificial intelligence, is inference. Given only noisy observations of the world, can we sort of figure out the rules governing the process that produced all of our observations? And right, this is what we do in a very shallow way when we cluster documents, in a deep way when we do things like grammar induction or when we train question answering systems just from question and answer pairs. And today we're going to be looking at this specifically through the lens of program induction, which is a sort of nice overarching framework for thinking about latent variable problems. And we're going to be specifically looking at how we might use language to build a procedure that can infer programs given input-output pairs for those programs. And finally, if we really want to reproduce all of the tools that people use for learning from language, we need to give our learners the ability to generate language too, right? For sort of models as we're training them to describe their current understanding of the state of the world, to ask questions, and so on. This is a big problem. I don't think I have an answer to the big problem, but I do want to talk about some very baby steps in this direction, specifically aimed at getting models to generate natural language descriptions of the features that they've learned so far in a way that can, in principle, support downstream understanding. And I'll say again, this is only something that's recently crystallized as an area of research focus for the group. This is sort of a grand vision that we've drawn on this slide, and we really just have the first pieces of it, but I'm excited to talk about those now. Good, so let's jump right into this, starting with the problem of learning from demonstrations, and the work that I'm going to be talking about in this section was really mostly done by Pratyusha Sharma, who's a PhD student at MIT in collaboration with her co-advisor, Antonio Torralba. And I think she's posting the paper before 2 today, so hopefully it will be on archive tomorrow. Okay, so we mentioned before cooking as a kind of canonical example of a family of skills that we learn, at least in part, from natural language guidance. And if we're going to do big, complicated things like cooking in the real world, we need to start with even simpler manipulation tasks in household environments, like finding our way around and picking up individual objects, interacting with really simple appliances and containers. And so here's an example from Alfred. I see Jonathan sitting in the front row. Alfred's great. He helped make it. Alfred is a simulation environment designed to do exactly this. Alfred tasks look like this. You have some high-level goal, like put a clean bowl of water on the kitchen island, and you have to train a policy that can interact with this sort of simulated environment to find the bowl. It's found a dirty bowl, and it's going to carry it to the sink and wash it, and then fill it with water, and it'll put the clean bowl on the kitchen island. So these are broadly the kinds of tasks that we're going to be interested, or that we're going to think of as prototypical for this setting right now. And even really simple tasks like these have a lot of moving parts, right? At the low level, we need to be able to recognize objects. We need to be able to plan paths between visible locations. And at the high level, we need to be able to reason about the long-term consequences of those low-level actions, right? That even a task as innocuous as cause the knife to be located inside the drawer requires finding the knife and grasping the knife, finding the drawer, opening the drawer, setting the knife down, closing the drawer. And even if we abstract away from the really, really fine-grained motor control that as a roboticist we might need to worry about, this is a relatively complicated sequence of steps that we need to take in order to accomplish really quite a simple goal. And this is a real challenge for modern machine learning tools. That if we don't try to model any of the kind of high-level structure that's depicted on this slide, and we just get 10,000 demonstrations of people putting knives in drawers and train a deep network policy or something to map from just these high-level goal specifications to and observations to sequences of low-level actions, this doesn't work at all, and you actually do quite poorly at these tasks. So what might a more effective procedure look like? And it might look something like this, right? That I'm going to have one model that takes one of these high-level goals and decomposes it into a sequence of these kinds of high-level subtasks that we named before, and then another model that's going to take these subtasks and decompose each one independently into a sequence of low-level actions that accomplishes it. And sure enough, there is a huge literature in reinforcement learning and learning from demonstrations on building hierarchical policies, hierarchical agent architectures that work this way. For the most part, they either require you to formalize the entire planning domain that you're working in symbolically and sort of hand engineer a planning mechanism that gets you from goals like knife and drawer to sequences of high-level actions. Or to predefine some fixed inventory of skills that your agent's eventually going to be able to deploy, collect a bunch of specialized demonstrations, one for each new skill that you want your model to have, and then train some policy either via imitation learning or via RL to chain these predefined skills together in the right sequence. There are also totally unsupervised methods for doing this that don't require kind of any supervision at this intermediate red layer at all, but they tend to find skill decompositions or task decompositions that don't do what people want at all, that sort of have weird boundaries and weird abstractions and don't generalize all that well to new tasks. And so, even after decades of research on this problem of building hierarchical agents is pretty hard. And here's where language is going to come in. What we're going to see is that natural language supervision can, in principle, give us a different way of training these models that simultaneously gives us control over the skills that are learned without requiring us to actually like pre-commit to a specific inventory of skills, or even, or I guess, or in particular, like hand-defined symbolic domain representations. The way we're going to do this, the way we're going to sort of use language to do a better job of learning hierarchical policies is something like the following. We're going to start with a data set of demonstrations, of high-level goals paired just with these low-level sequences of actions and observations. And now, rather than sort of predefining like a fixed finite inventory of skills, we're just going to ask people to come in and annotate these demonstrations with like natural language descriptions, basically instructions that you might give to somebody to cause them to produce one of these demonstrations. This is really nice in the case of Alfred in particular because there's like a separate instruction following task embedded in Alfred. This data is already part of the data set. Now, there are several important things to know about this supervision. First, these annotations that we're going to collect are just free-form language, right? There's no guarantee of consistency in how objects are named, in how tasks or goals are described across demonstrations or even within individual demonstrations. So I have no guarantee that the first time I pick something up and the second time I pick something up, I'm going to use the word pick both times. The second thing to notice here is that we're going to assume that we have no information about the correspondence between these natural language descriptions and the individual action sequences that they pick out. Right, so people are just sort of describing the sequences that they see demonstrated without like saying, minutes 1 to 2 of this video describe action 1 and minutes 2 to 3 describe action 2. So this is a pretty lightweight data collection paradigm, in principle pretty easy to get crowd workers to do it, although as I said before, we're just using existing annotations here. And most importantly, the assumption that we're going to make here is that we only have access to this kind of language data at training time. So at test time, we're assuming that all we get are these high-level goals, and we want to generate these sequences of low-level actions. And the hope is that having some amount of information about the high-level structure of these tasks, just when we train our model, is going to help us do that. OK, oh, I didn't mean to have an animation there. Even though individual annotations are easy to collect, getting a lot of them is still going to be expensive, especially if we have like lots and lots of demonstrations that we're starting out with. So we're actually going to make one final assumption here, namely that about our natural language supervision, namely that we don't have very much of it. So for all of the experiments that we're about to look at, we're going to assume that we only have annotations for like 5% or 10% of our data set of demonstrations. OK, so now we have a problem formulation, we have our environment, we have goals, we have demonstrations. At training time only, we have natural language instructions annotating a subset of those demonstrations. We want to build an agent that can get from goals to actions on its own. How are we going to use this data? Well, here's a picture of the policy that we eventually want to train, and this should look very familiar, right? We start with a goal. We generate some kind of abstract plan specification described in natural language. But now this plan specification, rather than being a sequence of symbolic subtasks or whatever, is a natural language string. And rather than defining a formal planning language or any kind of predefined set of skills, we're just going to let the agent use whatever language it can acquire from the annotations that we have at training time to build a high-level task representation and to kind of reason about its own future actions. And conditioned on this language-valued plan and also environment observations, just like before, we'll have some other policy that takes low-level actions in the environment. So this is a nice picture. It looks like all the other hierarchical policies that we had before. But how are we going to train it? Right? Because the situation that we find ourselves in at training time looks like this. We don't have natural language annotations at all for most of our demonstrations. And when we do, we don't actually know how these things line up with our subtask boundaries. In other words, we have some kind of latent variable problem, where on annotated demonstrations, the correspondence between these plans and actions is latent. And on unannotated demonstrations off on this side, on most of the data that we have, these high-level plan descriptions are latent themselves. And so at a very high level, what we're going to do is run some kind of learning algorithm like this. We'll make an initial guess about all of these values that we don't get to observe at training time, and then alternate between finding better alignments, finding better descriptions of each aligned segment of these unannotated demonstrations, and finally finding better parameters for this plan generation policy and for this action generation policy. Okay, let's be a little bit more formal about this. So here's all the different variables that we care about. We have goals. We have what we're going to call subtasks, these natural language descriptions. We have alignments that pair each low-level action with one of these high-level subtask descriptions. And then we have the actions themselves. And drawn this way, the sort of downward-facing arrows in this picture correspond to the two different components of our hierarchical policy, right? The planning subpolicy that generates these goals, or these subtask specifications, and the action subpolicy that generates actions. Just like this. And to train these policies, we're just going to do maximum a posteriori inference. We're going to find hard assignments to the missing subtasks, the missing alignments, and the model parameters themselves to maximize the complete likelihood of our data set of training demonstrations under this learned policy. And as I just sort of hinted in the high-level piece at the beginning of this, we're going to do this via coordinate ascent. So we're going to alternate between aligning pieces of demonstrations to instructions, relabeling each chunk of one of these demonstrations with the best possible description for it, and updating model parameters to fit all of the other variables. Now, a couple of these steps are interesting. To align actions to pieces of plans, we're going to, just like very briefly, introduce index-valued alignment variables, where every alignment variable tells me for a given action what high-level subtask it came from. And then we just find under a fixed setting of the policy parameters, find the highest scoring assignment to these things. If you're a speech person, this looks a lot like dynamic time warping. If you're a machine translation person, this looks like monotonic alignment. And we can use basically the same dynamic programs to solve it in each of those two cases. The most interesting piece of our inference problem here is this labeling phase. So remember that what we're trying to do here is impute natural language descriptions for segments of unlabeled demonstrations. And once you've fixed a segmentation, right, so I know that this group of actions are all aligned to the same subtask, this next group of actions are all aligned to the next subtask, you can think of this problem as inference in a hidden Markov model, where the emission distribution is this low-level action policy, and the transition distribution, conditioned also on the goal, is this high-level plan generation policy. However, it's a hidden Markov model in which the state space is the set of all possible natural language descriptions that you could assign to any sequence of low-level actions, right? So we can't run the Viterbi algorithm. This is totally intractable. Not going to get into the details today, but you can do some fun things with learned inference models to help you solve the inference problem in this space and annotate each of these segments that you found in the previous step with a natural language description. Okay, and then the parameter update phase is just going to be stochastic gradient descent. We fixed everything else. This looks like supervised learning. Nothing interesting to say here. Okay, so how well is this procedure going to work? What we're looking at on this slide is an example of what this model does at training time on one of these unannotated demonstrations. And the main thing to notice here is that just given the sequence of low-level actions and observations at various points here, this procedure that we just described is able to correctly segment this demonstration into pieces and label each of those pieces with an appropriate natural language description, right? That at step 1 it says find the butter knife, at step 2 it says pick up the knife that's on the counter, and so on and so forth until you've sliced the potato or the tomato or whatever this is and put it on the top shelf of the refrigerator. Okay, so this is doing the right thing at training time. We started without any information at all about the high-level structure of this plan, and we were able to impute all of this information in a way that at least superficially looks plausible as human observers. And here's what this model does at test time. Start with a high-level goal, place a washed pan on the counter, generate now, just from this goal, a sequence of natural language descriptions of the steps that you need to go through to put a washed pan on the counter, and then translate each of those into actions and execute them. And we'll see that pretty much this model does exactly the right thing. It washes the dish and then places it on the counter. Cool. So what have we done? At a high level, you can think of what this procedure does is as using language to induce a sort of library of reusable skills that are now available to this agent architecture at the high level for interacting with the environment. Where every natural language string indexes some skill that's available to this agent, and the planning policy can chain these strings together in sequence. And the main thing is that, in contrast to the way that we're used to thinking about hierarchical policy learning problems, this library of skills that we've learned is open-ended. It's compositional, it's extensional, or it's extensible if we just collect, a few more annotations for a few more tasks. And this is something that I would love to talk about more, but I'm not really going to be able to talk about in this talk today. It lets us hook into all of the things that modern language models can do to reason about the relationships between goals and tasks, or between tasks and other subtasks in sequence. And so, in these models that we were looking at on the previous slide, both the segmentation and the video, the model that's actually turning my goals into action sequences and my actions into, or my high-level actions into low-level actions, those are both pre-trained language models, like sequence to sequence, I think they're T5 or BART or something, language models that come to these tasks equipped with an understanding, a relatively rich understanding of the relationship between natural language strings, and this turns out to make a pretty big difference for doing well, even in this policy learning setting, where at the end of the day, we don't care about language at all. We get goals in, and we get low-level actions out. In numerical terms, I guess the first thing that I want to say, there's a big star on this slide, which is that all of the numbers that we're looking at here don't include results for the navigation subtask. I'm happy to talk about why that is later on, but if you're super familiar with Alfred, these are not exactly comparable to things that you've seen before. On all of the other subtasks, using just 10% of annotations, and in fact, if you only use 5% of annotations, the red bars are exactly the same, we do substantially better than ordinary behavior cloning, a model that just gets these high-level goals and low-level actions like we saw at the beginning of the talk. And in particular, if we compare this model to existing work on a much easier version of this task, these blue and purple bars, where we assume that we have access to full, detailed ground truth plan specifications for all of our training examples, and ground truth plans at test time, detailed instructions. We actually match several state-of-the-art approaches here. This is no longer exactly the state-of-the-art on the instruction following task, but the main claim that we want to make here is just that you can get very close to that using basically no language at test time or training time. And finally, we talked before about the fact that using strings as implicit representations of the library of actions available to you makes your library open-ended. A fun thing that we can do is ask this model to accomplish a goal that's never exhibited anywhere in this Alfred data set. Here we ask it to scrub some tomatoes. There's no scrub task in this data set. I think that should be scrub some apples. I think that's my typo rather than the model's typo. But it finds the apple. It generates some weird intermediate things. It says to find the apple in the trash can, which it may or may not actually be. But it knows that scrubbing is something that you do in a sink and that you do with water. And it's able to generate an appropriate sequence of high-level actions describing that. Even for things that are not part of this Alfred environment. Now, we don't know how to translate, scrub in the sink with water into low-level actions, but take this as some indication that we could, in principle, use what we know about the relations between strings and strings just at the high level to help us generalize to totally novel goals. Okay, so to summarize this section of the talk, what we've done here is describe how to train a hierarchical policy that reasons over sequences of high-level skills parameterized by natural language strings or indexed by natural language strings. We've showed that you could train these kinds of hierarchical models extremely sample efficiently by treating language mostly as latent at training time and learning most of what you know about language from offline language model pre-training data and a small number of labeled examples. And we showed that this works, right? That the resulting models are competitive with things that have much stronger supervision, that they generalize in non-trivial ways, even to sort of out-of-distribution tasks. I will pause here and ask for questions before we move on to the next section. Yeah?
Is the distribution of training samples you use, if only 10% of your tasks are annotated at training time,
Yeah.
is it highly sensitive to what that distribution is?
Yeah, so we haven't looked at that. Like all of the experiments that I was just showing is if you sort of sample that 10% or 5% or whatever uniformly from the larger set. I'm sure it is in the sense that if the model is never seen at the low level, like picking up two objects in sequence, you're probably not going to do a good job of inferring that at the high level because the language model is not going to like it. And so there, I think it's an interesting question, like thinking about specifically what's going on in this slide. How far can you actually push this? How much do you sort of need to see most of the distribution of like compositions or high-level tasks to be able to generalize in this way? And I don't know. Yeah.
I'm wondering how well this method can scale to more like complex tasks. Because in average, most of the step-by-step instructions are still quite close to the actions. For example, the go-to sync place is basically like go to the sync place and put this related to food.
Yeah.
What if we have very complex tasks like make me a meal, and the person just talks about, okay, cook me the pizza, repeat the pizza, something like that, in a very abstract way. So I feel like there's still a lot of work for the controller to do, given that high-level instruction. So I'm wondering, is it possible to make it like of deeper hierarchies that you get the abstract and you compose to lower level language, and at some places you ask the controller to initiate
Yeah. There are many interesting things in that question that I want to address in sequence. So one of them is that, like, in Alfred, how interesting are any of these subtasks? One of the cool things, I think I don't actually have slides for this, is that, yeah, most of these non-navigation actions involve pretty stereotyped, like the way you cook something in a microwave. You open the microwave, you place the object in the microwave, you close the microwave. If you break these tasks down, yeah, I don't have the task level breakdowns at all, but basically if you break all of these subtasks down by the number of different possible realizations, the number of ways of picking an object or placing an object, where this actually does best relative to the baselines is the tasks with the most variation in the number of possible realizations. So, in an absolute sense, definitely the sort of subtasks in Alfred are not that long. But I think within the sort of range of variation that's available on the data that we have, there's some evidence that that the trend is right. The bigger question is, okay, fine, this is a simulated environment with discrete actions. How do we actually scale this up to real robots? I think one possible answer there is that once you've reduced this to a pick and place task, motion planning is super hard, but it's also something that other people have spent decades of their careers on, and that even getting something into a form that looks like this gets us pretty close to something that roboticists can actually run with, or at least that will clearly require other kinds of solutions to solve than just imitation learning. So there's a part of me that wants to say not our problem, but it also does seem plausible to me that it's sort of if you really had low-level continuous control, that this kind of mechanism would be helpful for learning from demonstrations at that level. And we're talking to roboticists very soon. We're hoping to scale this stuff up, but no empirical evidence there yet. So yeah, great question. Yeah.
So when you're framing this kind of problem as this HMM style inference where you have some observed variables and some likelihood function of the interaction, there's a bunch of different ways in which the latents, or you could assign latents or predict latents.
Yeah.
So do you have any biases or priors that you're incorporating to try to prefer certain assignments, or does it just work out with the data that you have?
Yeah, well, so one very strong prior is that the backbone of this HMM, which is non-stationary, right? It sees all of the previous. Actually, that's not true. As we're doing it here, it's stationary. Never mind. It looks like a language model, right? So it does have preferences on pairwise tasks that can come after each other, and that's a pretty strong prior on the kinds of things that you can generate. Another thing that turns out to be important is getting the initial segmentation right when you start this inference procedure. Didn't talk about that at all, but we're using other off-the-shelf unsupervised segmentation techniques for discovering those boundaries. So those are probably the two important things, are having that backbone, which is worth 80-ish% on this graph, and then getting the initializations right, without which nothing works at all. Yeah?
Just a clarification, scrub would still be difficult if you didn't have an action corresponding to it at the low level thing, because scrub appears in the red in addition to the purple. Well, in that slide.
Yeah.
So will scrub some tomatoes.
Oh, that looks purple on that screen.
Or maybe blue.
Yeah.
But then you also have put an apple and scrub it with water, so if you don't have a scrub action in your low level.
Right, but this is the I hate saying this, but this is the language model magic, right? That this is like the model that's generating these sequences of high-level tasks from of subtasks from goals has never on the Alfred training set seen scrub here and scrub there, but it's seen it in open domain text, and so it knows that you can copy. Does that answer your question?
Well, I guess.
Oh, and then there's the like, how do you get from here to like low level actions and finding that correspondence?
Yeah. So like, if you don't have a action that realizes scrub in your robotic controller,
a low level, yeah.
It'd be out of line with this.
Yes. Yeah. No. Absolutely. And then you need. Be like, you can do this end to end and it works, but just that. There's enough information at the high level here to generalize a bit. Yeah. Yeah.
I was wondering if like grounded documents can help with coming up hierarchical structures. Let's say in the case of microwave, if we have a grounded document for microwave tutorial, like manual for using that, so can that help in coming up with these tasks?
Yeah, meaning like if we had access to other kinds of supervision that's not big text corpora and not like specifically annotated demonstrations, could we use this? Like, yeah, absolutely. And I think there's a wide.
Have you tried it, or like, do you have any insights from it?
Yeah, I mean, I think like we were saying before, Alfred, the microwaves are not real enough for there to be anything for you to learn from a microwave manual, but we are, yeah, I guess looking at other kinds of supervision that you can use in these places, but pretty preliminary. There was one other thing from one of the other previous questions that I wanted to say again, which is, could you do deeper hierarchies as a way of doing more complicated tasks? And like, yes, very naturally, now when you're at this stage, you're doing something that looks like inference in a CFG with an infinite number of states instead of an HMM with an infinite number of states. And if you could get that kind of annotation, or even a small amount of that kind of annotation, then you could like, yeah, parse low-level action sequences into entire trees. And that would be super cool, and I hope we get to do that at some point. All right. Oh, there's a question in the chat. Oh, hi, Daniel. Question in the chat is, what parts of this graphical model condition on the environment observations do you need to see the environment to know that your instruction should include sync? That's a great question. So we have played around. So the inference network that's doing this stage right now, well, so I guess this matters in both directions. Like when you generate a high-level plan, we're actually generating these in an open loop way. You see the initial environment state, but nothing else. And when you do the inference procedure, I think you see the actions and not the observations of the environment at all. In more complicated environments or noisier environments, you would certainly have to do like closed loop control. But for these tasks, it worked well enough to do it open loop. Good. All right, then let me move on to the next section of this talk. Which is, in fact, not so different from what we just looked at. The question that we're going to try to answer here is whether we can take this machinery that we've developed and apply it to other problems, specifically problems where we care about the values of these latent variables that we're inferring themselves and not just the predictions that we're getting out of our model at the end of the day. We're going to do a little time travel here. We're presenting this as an extension of the previous approach, but this paper was published earlier in the year. Good. So a canonical example of one of these kinds of inference problems, and something that actually provides a sort of nice unifying perspective on these kinds of inference problems, is program synthesis. And so what we're going to try to do now, rather than going from a goal to actions, we're going to go from some kind of specification, like this input or this image that we're drawing on the slide, and this might be an image that we want to generate. It might be a set of test cases that we want to satisfy from this specification to a program that satisfies that specification. And this comes up all the time, right? It comes up in inverse graphics where we want to de-render scenes. It comes up in text editing where we might want to, provide a couple of examples of a transformation we want our text editor to apply and then have it applied everywhere else, and many other domains. And as before, doing well at this program synthesis task is really all about abstraction and composition. Just in the way that the plans that we were looking at in the previous section are compositional, programs are super compositional, right? If I have a family of related graphics programming tasks or text editing tasks, I expect pieces of those programs to get used over and over again. And if I can identify and name those pieces, then the space of programs in which I'm going to have to search to find a program that complies with one of these specifications is going to become much smaller. That if I sort of have the right functions in my library that I use for search, then it becomes easier for me to write programs that are both complex and natural and satisfy sort of natural human goals. And the state of program induction right now is actually pretty similar to the state of hierarchical policy learning, in the sense that there are things that work super well if you carefully engineer a domain-specific language for your graphics domain or your text editing domain of interest. There are things that work sort of okay in a fully unsupervised way, starting with something that's very close to raw lambda calculus. This is pretty miraculous on its own, but you wind up with some weird-looking library functions. And there really aren't good procedures for automating discovery of reusable functions that look like the kinds of abstractions that human programmers produce, like the F1 and F2 that we've drawn on this slide. Okay, so maybe unsurprisingly, how is language going to help here? Well, as before, these sort of human-like abstractions are precisely those things that we tend to give names in natural language, the kinds of things that we tend to abstract as reusable subroutines when we write programs. And so the hope here is that language can again provide some kind of lightweight, distant supervision about the compositional structure that we want to infer in programs. And in fact, we can tackle this inductive program synthesis problem using a model that looks pretty similar to the model that we were looking at in the previous task. And so we're going to imagine, again, a generative process in which, for example, natural language annotations give rise to sort of individual reusable program fragments via unobserved alignments, and that those things compose together to produce full programs, and then that we execute these programs to get the outputs or the input-output pairs that we observe. One very important difference between what we're going to do now and what we were doing in the previous problem is that we're going to observe only these outputs. It's the programs that we're trying to infer even at training time, and even at training time, we're not going to have access to any ground truth programs. This is sort of like the defining assumption of inductive program synthesis, that you get no programs to start with. And it means that we have one more latent variable to deal with, namely the one that we actually care about, the program that we're trying to write. When am I supposed to stop? 2:45. Okay, great. We got tons of time. The basic story is going to be basically the same, right? That we have some set of annotations and some program outputs that we observe, and we're going to try to infer alignments between these natural language annotations and the programs, and then we're going to try to infer the programs, and then we're going to execute the programs to get our answers. The generative story looks a little bit different here in that we are actually now going to imagine not generating programs conditioned on these strings, but jointly generating paired programs and natural language annotations. And so we're going to try to learn up front just like a generative model, a prior over programs and the strings that people write for them. And what we care at the end of the day about is not sampling from this prior over programs and annotations, but instead doing sort of inference in this posterior inference in this model. But we're still, during our parameter update step, going to be trying to learn this generative model of programs and strings. Once we've sampled a program from that generative model, we just execute it. And we assume here that execution is totally deterministic. I can take any program that has been provided to me in this way and get an output, like an image in a graphics drawing domain. Okay, and one detail that's going to matter here is the specific parametric form of this generative model of programs and strings. And in particular, we're going to imagine that our generative model over programs is backed not just by sort of continuous parameters like the policies that we had before, but by a discrete library of functions. And that the way we sort of sample a new program is we compose these functions together in ways that are allowed by the type system of our language. Whenever we compose two program fragments together, we also compose together their associated natural language descriptions, and this induces a joint distribution over programs and strings. And now, we want to do posterior inference, and we're going to do it, or rather, we want to learn in order to be able to do posterior inference later. As before, we're just going to do this by maximizing the complete likelihood, fixing our annotations, fixing our programs, leaving the other things latent. And just like before, do this via coordinate ascent. Now, it's the parameter update step in this problem that becomes the interesting part of this procedure. When we update this model, having fixed a bunch of programs, we're going to do it by adding new functions to the library to increase the probability of our data set under this composition that we described before. You can give this a probabilistic interpretation, but I think actually the easiest way to think about it is in terms of compression. That we're going to formulate this objective in such a way that when we do the parameter update step, what we're trying to do is to minimize the total number of bits that it takes to describe both our data set in the most compact form that we can express it and the library that we use for doing that expression. That's a lot of words. Let's look at an example. Suppose I have the following 3 programs and the following 3 annotations. Don't worry yet where these programs come from. So I have programs, and I have labels for each of these programs as strings. If we look at these 3 programs, we can observe the following. We can observe that there's a repeated fragment in all of these programs, and that repeated fragment is always present when the word gone is present in these programs. In fact, there are other repeated fragments here, right? Rotate 72 shows up in the middle example and the example on the right, but there's no corresponding natural language string that ties those 2 things together. But what we do see is that, there's this chunk that we're drawing in yellow, and whenever we see the chunk in yellow, we see the word gone. So we'll now do the following. We will abstract from these programs and add to our new library a function that contains exactly this program fragment that says, forget about the number 7, forget about the number 51, give me lambda of those 2 numbers that gives me the fragment drawn in yellow, and associate this with the word gone. And once I add this to my library, I can rewrite my training set in the following way. I can replace that whole big chunk of code that I had in each of the examples with the word f0, or with the function f0, and I can replace the word gone with the name f0 as well. And what this means is that I've reduced the total size of my training set, right? I now have to store just 1 copy of this gone function in order to express both of these programs that we have down at the bottom. And because it was the presence of the word gone that signaled that I was allowed to do this, I've effectively used my natural language annotations at this stage to help me discover a reusable program fragment that does polygon generation as opposed to a probably less reusable program fragment that rotates me 72 degrees. And this is important because now when we get to this search phase here, the thing that's new, the thing that we didn't have in our policy learning setting, we're going to use these new library functions when we do this search. So the goal of search, right, is to find programs that execute to the right value. This is a binary criterion, and at some level there's like nothing that you can do other than enumerate programs in some order and guess and check. But if you enumerate these programs in the right order, if you enumerate the sort of, more human-like programs or the more human-relevant programs first, then you're going to have to search for less time before you actually find the right answer. And so here, having these functions in our library is going to allow us to preferentially generate programs that contain fragments that people consistently labeled with natural language strings. Program fragments that seem to correspond to sort of high-level abstractions that are available to us in language. And this is going to sort of let us find more complex programs, provided that those programs reuse code that we already found useful somewhere else. Okay, so what does this learning procedure look like in practice? Remember that we start with a bunch of outputs, and here we're looking at graphics, sort of turtle graphics programs and their natural language annotations. We've collected for this task data sets of real human-generated annotations and also synthetic annotations from a grammar. Story is basically the same in both the cases. And we start by searching. So we start with some very primitive graphics drawing library, basically like Logo or Scratch or whatever, as you may have seen it a long time ago. And we'll start by looking for programs that generate our training specifications just in this base library. And this is really hard. We're going to fail to, after searching for a really long time, fail to find the right answer on most of these tasks that we're looking at the bottom. On those, we'll just give up. But maybe on this task that we have all the way at the right, the triangle task, we find a program that draws a tiny triangle. And maybe we do this for a bunch of, a program that draws a tiny square or a program that draws 2 tiny triangles or something. And we see that there's a reusable gone type function that we can abstract out here. I think this is actually a program that draws a small line, but something like that. So I've expanded my library during this parameter update stage, this compression stage, and now I go back and maybe my improved library helps me solve more of these problems because they're closer to the top of the search space. And once I have more program fragments, I can compress them again. I can memorize functions that call out to other functions that I already memoized. And if I repeat this procedure long enough, eventually I'll be able to solve a large fraction of these programs. 2 things that I want to note here. The first is that the sort of basic mechanism underlying this compression procedure is not actually new in our work. It's from a really beautiful paper called Dreamcoder by Kevin Ellis and colleagues from Brain and Cognitive Sciences at MIT last year. Basically what's new algorithmically here is noticing that we can actually use language to drive this compression process in a way that gives you better, more reusable library fragments. There's also just a ton of other cool stuff that goes on under the hood that I can't do in the time limits of this talk. The coolest one is that this compression procedure can actually refactor programs in pretty non-trivial ways to make them more compressible, and that happens automatically in this compression loop. And we have also added to this prior a bunch of linguistically informative priors that prefer alignments and prefer program libraries that respect sort of pragmatic constraints on language use, like that you don't use the same word to refer to 2 different library fragments. And finally, during the search phase, we're actually conditioning on the language when we have the language available. We're conditioning on the output when we have the output available. And we're using a learned heuristic to help us explore the search space. And that helps in addition to the sort of shrinking of the search space that results from adding programs to the library. OK. With all those details aside, I encourage you to read the paper. This is the basic skeleton of the procedure, right? Just coordinate ascent on our missing variables like we saw before. Parameter update is compression. Compression is driven by sort of reuse in language. OK, how does this work? So we've evaluated on several different data sets. There's a sort of turtle graphics domain. There's some visual scene reasoning over graphs. There's some text editing tasks. I'm just going to show you results from the graphics domain. These are what the training examples look like. So a relatively diverse set of complex images, but images that have sort of natural symmetries that people are able to describe very easily. These kinds of snowflake shapes, these rows of repeated shapes, and so on and so forth. And if we just throw this procedure that we saw before at a data set of shapes that looks like this, we are able to solve some of them. We infer programs for pretty non-trivial graphics tasks using library functions that we've learned. And in particular, if you plot just at training time, the fraction of training examples for which you have successfully inferred at least one program that does the right thing, using this side information from language lets you solve a substantially greater fraction of programs than using the sort of base Dreamcoder synthesis algorithm, which is the state of the art on these tasks right now. And the coolest thing is that the libraries themselves actually look pretty meaningful. We get all these reusable functions, like one that draws n-gons with sizes with an edge of a fixed size, and we do in fact label it with the word gone, like we saw in the examples before. We learn things that draw these kind of snowflakey shapes that put polygons at the end of arms. We learn staircases and zigzags, and so on and so forth. So you really do from language not just get the ability to solve a large fraction of these tasks, but actually to learn reusable library functions. And you can then take these library functions and even do non-language conditional synthesis on downstream tasks. And it helps you do better, like we saw before, at test time, even when you only have language at training time. OK, so what we've done in this section is basically just extend our approach to policy learning to solve latent variable programs posed as program synthesis problems. And we saw that in particular we could just hook that learning algorithm that we had before up to an existing state-of-the-art program synthesis algorithm and do language-guided program induction and library learning. And just as before, language sort of tells us the set of primitive things that should be in our library that we use for reasoning about what the world looks like. And this helps you solve a bunch of pretty challenging program induction problems. Pause for questions again. Yeah?
So the symmetry between the learning program synthesis and learning hierarchical policies is really neat, and I think you can do this with almost the same approach. It sounds like there's one
Yeah, so is there a reason that in the policy learning setting we're sort of restricted to sequential policies, whereas here we can sort of compose things hierarchically? No, and this relates to the question that we had before, could you do the policy learning thing hierarchically? You absolutely could. I mean, I think, like, in some ways the more salient distinction is that we're trying to learn the execution model in the previous task, and here somebody's given us a fixed execution model, and in some ways that makes it easier because we come with like a really strong inductive bias provided by the library. In some ways it makes it harder because now we have this like insane latent variable problem, whereas previously we could just learn like a seek-to-seek model that turned strings into low-level actions. And like everything in this intermediate space is interesting, right? You could have policies in the policy learning setting expressed as symbolic programs like this, which is something that planning people think about all the time. You could have versions of this model where you can replace little fragments inside this program library with neural nets that just say, well, I don't know how to do this symbolically, but give me an image and I'll give you an image out. And you could learn deeper hierarchies like we were talking about before, where when you parse a demonstration, you don't just segment it, but you actually figure out the whole like tree of relationships between things that are there. Yeah.
When your method learns that gon corresponds to a particular function, how do you decide what the arguments are, and are there cases where you get the arguments wrong? Because that would be an error that would propagate, right? So, I mean, other functions who want to call gon might not be able to because
Yeah.
the number of arguments is not.
Yeah, so the question is, how do you make sure that when you abstract out a gon function, you really abstract out a generic n-gon function and not like the 5-gon function or the 5 or 7-gon function or the pentagon function with like sides of a fixed length. In fact, you do. Like the first time you abstract out that function, you probably do just abstract out a pentagon function. But every time this compression algorithm runs, it can say, oh, well, I have a the pentagon function here and the heptagon function here and the octagon function here, and I could shrink this data set if I abstracted them out one more time. There's like deep magic that lets you actually do that refactoring algorithmically, where basically you have this sort of, you for each program construct a graph that's a packed representation of all of the possible lambda abstractions of that program, like factoring out different functions in different places. And then you sort of take the packed forest that you have for each program, and you hash them in a clever way that lets you figure out where there are collisions between nodes that exist in different programs. And that's what gives you a candidate for compression. Yeah, so this is like also very deep and also something that we very much cannot take credit for, but I encourage you to read the Dreamcoder paper because it's super cool. Yeah.
So first, with the preface, this is very interesting. I had one question about the thing you mentioned first, which is program synthesis relies very heavily on DSLs, very heavily specified DSLs that give you a chance in the first place of ever getting the correct answer.
Mm-hmm.
And it seems like the method that you're proposing here still relies on that because you won't get anywhere if you never get anything right at the very beginning.
Yeah.
So like, what do you think the way forward?
Yeah, well, so I guess I would say what makes it work here and what doesn't make it work with generic search procedures is not having the right DSL as so much as having the right curriculum. Mm-hmm. Right, because here we can solve a bunch of easy examples. We can say these easy examples are all doing the same thing, add them to the library, and now the search procedure gets easier. Whereas if you're in a sort of normal, like deep learning for program synthesis task where you just sample a bunch of things from a prior, you learn an inverse model, the most complicated programs are still going to be complicated because there's not this compression phase. So yeah, I mean, it's not like black magic, but I think the difference is that you get that ability to bootstrap yourself from having the right kind of data set instead of having the right kind of DSL. And the hope is that for natural problems, that's an easier thing to do.
I'm thinking, like, what if you put it in a situation where it was like, okay, I'm giving you Python, and now I'll give you 500 things that I would like you to do. I'd like you to build a web server. I'd like you to, and that's a thing where you don't even know where to start most of the time.
Yeah.
Like, do you think this has a chance of doing anything there, or like, would it be able to find a curriculum on it?
Yeah. Well, so I mean, whether it's able to find a curriculum on its own depends on whether you have the data from which to construct a curriculum, and then sort of naturally you solve the easy examples first. But like, I don't know, when you learned to program Python was the first task you were given, write a web server, or was it?
I mean, Graham, yes.
Yeah.
The rest of us.
Graham just, emerged from the womb able to write a multi-threaded.
But I guess my point is I had supervised examples.
Yeah.
I had, this is how you do this,
Yeah.
and this is how you do it in Python, and
Yeah.
this is relying on not having those examples.
Yeah.
And I was just wondering, like, if that's the way to go, or do you want to assume some supervision before you go into the harder?
Oh no, I think like in the real world you want to assume some supervision. Yeah, and that integrates naturally here. You do it semi-supervised in the same way that we did before, but our collaborators are PL people, and PL people like to solve this problem with their hands tied behind their backs. So, yeah, no, but that's a great point. Like you can and should do everything in a semi-supervised way. Yeah.
Sometimes when I notice, like when you draw the nested squares or circles are going in order, and the nesting could happen in a number of ways. So how do you handle those? Like, what I mean is that maybe like are ambiguous. Like for example, when language especially is ambiguous, how do you tackle that?
Yeah. Okay. So two things. Like one are the sort of surface forms of these programs one-to-one with their representations as compositions of pieces. If you've seen like a tree substitution grammar or whatever, there's the same problem of spurious ambiguity there as here. Second, what do you do, especially when that correspondence with language is ambiguous? So the answer for all of those things is that we just like marginalize out the spurious ambiguities. So the compression procedure actually looks at this program and sees all of the different ways of building it from different library fragments, and even like rewrites that are not explicitly provided in the library but that are licensed by the language. As far as ambiguity on the language side, we can actually tolerate it. This is a probabilistic model. The actual sort of generative process is you sample a program, and then you sample descriptions given programs, sort of amazingly under IBM Model 4, and that works pretty well. And so to the extent that ambiguity is allowed in that like lexical translation process in IBM models, then it's allowed here. And the compression procedure wants to in fact, maximize the likelihood of the data set.
The second question is more for fun. I don't know whether you have encountered any examples where your compression algorithm actually ran into an infinite loop.
I think the compression algorithm can't do that. Like it's structurally prevented from abstracting a program into a version of the program that it's already seen before and then trying to rewrite it back into its other form. There's certainly places when it gets stuck, right? Like we are not getting to the 100% point on this graph, and like the failure cases are not all that interesting to draw because they look like the ones that we get right, but we are not. There's both like high stochasticity in individual runs of this algorithm, and we're not getting to 100% in any of the runs. And these numbers don't mean anything in an absolute sense because it's a made-up data distribution. But like algorithmically, you don't get into settings where it is no longer possible to compress. One interesting thing that does happen, though, is that you can, and this is sort of related to the question before, you can get into a setting where the search procedure sees in one example that it's supposed to draw a circle and draws a clockwise circle, and sees on another example that it draws a circle and that it's supposed to draw a counterclockwise circle. And there's no way in our refactoring procedure to notice that a clockwise circle and a counterclockwise circle are the same. This problem is in general undecidable, so we sort of shouldn't expect that to be the case. But it is something where actually like noticing that induces an ambiguity in language should be a key that you should maybe try more aggressive rewrites of one of these examples, right? That if I'm using the word, it would be very surprising if in our language there were actually distinct clockwise circle and counterclockwise circle concepts that we didn't distinguish between linguistically. Therefore, if you find yourself in the situation where there seem to be two concepts with the same name and they look visually similar, you've probably done something wrong algorithmically. I don't know that I have a great like solution to that other than doing a brute force search on those particular cases, but that would be pretty interesting to look at. Yeah.
You talked about how the kind of search problem is really difficult because it's just a binary, like, did you get this right?
Yeah.
Is there a reason you're kind of not using visual features here to inform that search problem?
Yeah, so we actually are. Like when we do that search, there's a, and this is another like thing that gets inherited from Dreamcoder. In between the parameter update and the search phase. So I guess, first of all, the parameter update and segmentation happen simultaneously. Between the parameter update and the search phase, we actually draw a bunch of samples from the prior with the current library, and then train an inference model in the opposite direction that conditions on both the text and the image and tries to reconstruct the program that generated them. And you can get as much supervision as you want for this, assuming your current libraries are sort of properly specified, and then we use that heuristic to parameterize actually a very simple model that does the search, that places like bigram probabilities on like bigram transitions between program tokens, but that helps a lot. Yeah. Yeah.
Question, does the domain-specific language have the control flow operations like details and
Yeah, so I think the language that we use for these is basically Logo. So it has control flow. Possibly it just has while or goto. I don't actually remember the details of the low-level language. You might be able to infer it from. There's a 4. Okay, so there's a 4. Never mind. Yeah. Okay, then maybe it's not exactly Logo, but.
It's about 10 minutes left.
Okay, cool. Then I will, I guess as expected, go very quickly through the final portion of this talk, which is a pretty different problem, namely the problem of generating natural language descriptions of things that have already been learned, as opposed to using language to supervise them. If we're going to use language as a teaching tool, we should also be able to use this language model to probe how well our teaching is working, right? To ask questions like, what is it that this neural network that I'm trying to train has actually learned about my task? This is a very hard question. I don't know how to answer it. Let's look at something easier and ask about individual features. So I'm training a neural network. I want to look at an individual neuron and figure out what is the function of this individual neuron. So how might we go about answering this question, even in the most abstract sense? Well, what does a neuron do? And what a neuron does fundamentally is it responds to inputs, or in like a convolutional network, to particular regions of inputs. So we can think of neurons, if we cut away the rest of the network, every neuron is its own classifier, but it's a classifier for an unknown class. And the first thing that we can sort of do if we want to understand what one of these neurons does is just say, okay, give me the positive examples of the class that it recognizes, give me the negative examples of the class that it recognizes, and let me try to figure out what that classifier actually is. And so, this is something that you can do. Here's an example of a real neuron in a data set trained for the MIT 365 places classification task. And you can see from these examples that this is a lamp detector. This paradigm is hard to scale up, right? It's sort of cognitively demanding to look at sets of images and figure out what's going on. In practice, you don't actually learn everything that this neuron does just from looking at 4 images. You want to be able to look at large sets of them. And if we want to answer even bulk questions about what kinds of concepts in general does a given network respond to, this is hard to automate. So another thing that you can do, and that's been invented many, many times, is to say, let's look at this neuron's response on a data set of examples where I've already gone in and sort of hand-labeled individual examples or regions of examples with the specific concepts that those contain, right? So I can take my lamp detector, I can just overlap its predictions with images where I've labeled all of the objects with object categories and try to figure out which of those object categories picks out regions that overlap most with the regions that this neuron responds to. Sometimes this works. Here, another real-world example, you look at this regions, you label this neuron as a lamp detector. Sometimes it doesn't work. So here's the same, sort of recognizing class-selective neurons procedure applied to, to some other neuron in the same network. It labels this neuron as a bull ring detector, even though it's pretty clearly not. It's like a generic sports field detector that responds to a volleyball court, a baseball diamond, a racetrack. So to the extent that we think we need more complex labels, like generic sports field detector, in fact, what's going on if you like run a version of this procedure I'm not going to talk about on this neuron, it responds to all sports fields except for football fields. Oops, what did I do? You know, and to the extent that we want to be able to generate labels like all sports fields except football fields, what we really want is the ability to describe these things in some sort of expressive, compositional, open-ended language, namely language. So you can do this, right? You can train a model that basically maps from these like tabular representations of neurons to natural language descriptions of these neurons. It basically looks like an image captioning problem. You need special kinds of data. It actually helps to use a sort of information theoretic objective for doing this decoding, but you know, forgetting about all of those details because I don't have time, this is an image captioning problem, right? Go from regions in which a neuron is active to human-generated descriptions of those regions, scraped from human-generated descriptions of just like random image patches that you sampled. And this like works pretty well. So here are some of the examples of the kinds of descriptions that you can generate. Horizontal lines on bottoms of objects, birds and poles, items with circular features, fluorescent yellow objects. So like, you know, in fact, a relatively rich compositional language for talking about what individual neurons do. They capture logical structure like disjunctions. They capture relational structure like bottoms. They capture, you know, complex modification like fluorescent. It doesn't work all the time. Bunch of different interesting failure cases. Here's something that labels as white areas on animals that I can't actually even remember what this is. But it's not exclusively, you know, there's like a patch of a white animal and a bunch of other things. It fails to be specific. It says buildings and sky instead of skyscrapers. It thinks this pizza in a GAN is just a corner. Who knows why? But this procedure still works well enough that we can do some non-trivial things with it. One non-trivial thing, I think the only example that I have time for in this talk is, you know, you may have seen when this OpenAI clip model came out, does great at assigning or pairing natural language strings with images, but is susceptible to this weird adversarial attack where if I take an image and I draw a different word on top of that image is now going to be classified as the word rather than the natural language string. And one thing that you can do with this procedure is, say, reach into a network that suffers from this vulnerability. We haven't actually done it for CLIP yet, but for some sort of laboratory versions of it. Find all of the neurons that talk about text and just cut them out so that this neuron model, in effect, can't see text anymore. And if you do this in the right way, you can actually decrease the susceptibility of these models to this text-based adversarial attack, in particular, by a small margin. Here are some real-world examples of it working, where the base model classifies them as a car and a chihuahua, respectively, and after ablating the right text neurons, you get the right classification labels instead. There's a bunch of other stuff that you can do with this. We just last night got a result where you can get versions of ImageNet with all the faces blurred out, and they're supposed to be sort of stripped of sensitive information about people. You still find in those models individual neurons that are gender, or I guess sex specific in their response to individual faces on unblurred faces, even though they have never seen a real face before. That's kind of cool. But I think the most important thing is that this gives us a first step towards a tool that lets us do auditing really at the network level, right? To be able to say, in the context of an individual decision, or even in the context of just some model that I've trained, can we answer the big questions that we started this section with? What are the surprising things about this model? Like the fact that it can't tell the difference between animal faces and wheels, or what are sort of sensitive aspects of the prediction that this model needs to make, like the thing that it thinks it has a human skin neuron inside of it, where we would really like to know what that model thinks human skin looks like and whether it actually matches the distribution over human skin tones that exist in the real world. So, very briefly, you can generate natural language descriptions of deep networks. It works well enough to do some interesting things and is hopefully a step for more model level interpretability. Okay, I will wrap up there. So just to sort of summarize today's talk, have presented methods for using language as a tool for training and at least superficially understanding deep networks. We saw that we could use natural language annotations to guide policy learning, to guide program induction, and even to label neurons inside deep networks. And I hope this at least sketches a skeleton of a path towards that picture we had on the right at the beginning of the talk of the girl with the book. That language could be and should be a first-class tool that we use for training the kinds of big machine learning models that we use today, and that we actually have like the pieces of the toolkit that we might need to do that. And I will wrap up there. So thank you very much.
So I guess we probably have time for one question, whoever raises their hand fastest. Okay.
In addition to enabling auditing, do you feel like this approach to interpretability will allow you to come up with customized compressions of larger pre-trained models for specific domains?
Yeah, I mean, I guess, so maybe, but like, in order to actually do even this procedure right, you need access to a validation set where you can make sure that you haven't totally destroyed the network by, because it turns out that if you have like an edge detector in the first layer of the network that's incorrectly classified as a text neuron, then your classification accuracy goes to 0 because now nowhere in the model can see edges. So I think if you're in a setting where you know enough about the domain for which you're trying to compress that you have examples of images in that domain, you probably just want to do that. I could maybe see this being useful for helping you make sure that you're not like overfit if you have a small number of those examples, or at least, as a way of like flagging, hey, you're about to delete this neuron that we think is actually pretty important. But I would be surprised if you could make it work just on its own.